Hi, now we are going to start with some interesting features of Freecad, which is all about finite elements modeling. So in order to do our simulations, let's begin with Freecad again. That's the starting session, so to speak. So of course we need to create something new, but before going to that, we're going to use a couple of different programs. So one of the programs that we are going to use is called Gmesh. So Gmesh is, I have it here, has its own website, and the website is gmesh.info, so it's gmsh.info, and it's an open source program which is used for triangulation or for meshing. So we need to have the mesh of the structure, and therefore we can use Gmesh. And you can simply download it, so it's technically speaking for all operating systems, Windows, Linux or Mac OS. You can get the binary files, it's the code which is already compiled and ready. If you are interested to have a look into the source code, it's also here because it's open source. You can really have a look into the source code, so you know exactly that the program is not doing anything harmful and it's only doing its job. This is the beauty of having open source. So if you have downloaded this, then you need to tell Freecad where it is. So in order to do that, so first I'm going to create something new and go to this module which is called FEM, right? So first I'm going into the module, and after I'm in the module, so I can have a look in the edit and preferences. Okay, so if I do that, then on the preferences, because I was in the module first, I will see here also FEM. Okay, so if I click on that, then you see here a bunch of different external programs for Freecad, and the second one is Gmesh. So if I click on the Gmesh, I have downloaded it to my folder downloads, and after downloading it, I'm showing into that that's the extracted stuff, and inside there is a bin directory, and in the bin directory there's a Gmesh binary file which is like this one. So I'm showing to that one, such that later on if I click on the Gmesh, so Freecad knows where it is. Okay, so you don't have to do that. So if you have installed as a system stuff in Windows, or most of the time also in Mac OS, you can do that as well if you want. I prefer not to do it in order to have different versions of that. So if you want to have as a system specific program that you have installed, then you can tell Freecad to search for the known binary directories. These are like depending on the operating systems, like /bin or /program files or something like that is the place where if you install a program, put the binary file there as well. So you don't have to show it as I do it here. This one is a little bit more secure because then you exactly know which version you're using. You can change it later if you want. Okay, so that's the Gmesh part. And also because since we are here, I can have a look here in the Calculix. This Calculix is something that Freecad is already have installed. So if you install Freecad, then this Calculix is also coming with that. So now we are going to use that one as well. But there are also other options like Elmer and Miss. I don't have them. Z88, and there are also a bunch of materials that Freecad is bringing it in. So, but we're gonna come to that. There's also something interesting in general. This is, by the way, especially interesting for macOS users, because this may lead to a problem that if you start using it, then it's difficult to find out what the problem is. So you can normally in the default setting, it is not like that. There's like a temporary directories, and the temporary directories, for example, for Windows, you can just use it, so there are no huge restrictions. But in macOS, there are a lot of security type of restrictions, so it is more difficult for Freecad to use temporary directories. It depends on the version of your operating system, but you may have a problem of if you just want to use the default settings and start Freecad. Once in a while, if you want to solve or do something useful, you cannot do that. So then, technically speaking, what you should do is you should use a custom directory where your computer or your user have access to write in. So I have chosen a custom directory here, which is simply on my desktop. There's a FreeCAD path, so you can just create a directory and show this here. Then everything, that means the meshing, or if you want to solve something, the solution and so on, will be saved into this directory. So that's what it means here. It may be also beneficial to have a custom directory, because then you know where the stuff is. Otherwise you don't know exactly. It's difficult to find out where it is. So you can say apply or okay, because doesn't matter if you say apply, then the window stays there. If you say okay, then the window closes. Okay, so before this was actually necessary, I had to go to this module FEM in order to, if I open the preferences, I have this options. So, but technically speaking, I don't need that now. I need to do a part. So let's do as simple as possible. Why not to start with a beam? Okay, so I'm gonna make a beam. So for that, of course I can go to part design and then say, okay, there's a two-dimensional structure, and then I want to extrude that. But if I want to have really simple a beam, then I don't need this longevities. I can simply use the part and use one of these primitives. So just to get it, so I have a cube. Okay, so because I want to have a beam, I want to make it longer. So by the way, have a look in the unit. So we have here in millimeters, so that's important. I'm gonna put like 100. It's a thick beam. It's not a real Bernoulli beam that you learn in mechanics of materials. This is more like a thick beam. So for this we cannot use beam theory. So even if I do simple bending, I cannot use beam theory because it's too thick. So if I make it more longer or slender, so to speak, then I can use a beam theory. But other than that, I need to use a three-dimensional calculation, which I'm going to do here as well. Okay, so here's the geometry. And if I have a look into this geometry, what I want to do is I want to clamp or hold one side and then do something on the other side. Okay, so I can really simply think of a beam bending. So that means I can hold it here on left and put a force on the right. So I need to go to this FEM and start the analysis. Okay, so now I'm in the FEM workbench, and here bunch of icons we're gonna use, and on the very left here there is an analysis container. So this numerical analysis, because of this it's called analysis. So you can think of FEM analysis. So this is why we have an A. This is the only button I can choose, by the way. So here on top you have the same stuff on the model. You have the analysis, or also mesh and solve and so on we have as well. So I'm going to choose the analysis container. Now I have it. Nothing happened. So I can have a look what is inside. Right inside there is something solver. You remember we talked about the Calculix. Next to the geometry was Calculix. So this is CCX is for Calculix. So there's a solver. So this solver is used for FEM, and there are bunch of different possibilities here. So I can double click on that and you can see this is a mechanical analysis. So that's the default case, static mechanical analysis. There are other stuff as well. Okay, so but I will keep that one. This is what we want to have, and say close. Now after I have the analysis, what I need to have is now you see the icons are possible to choose because I have an analysis now. So what I want to have is a material. So this beam, this structure is out of a material, so we need to define that. Technically speaking, the material has properties, so I can put the properties here, or FreeCAD has some materials already inside. We can choose one of these materials as well, because it depends on what you want to do. If you want to use a wood material, then you can choose that one. If you want to use a steel, there are different steels, but you can also choose the steel generic, or there are also a few more alloys like aluminum, magnesium, or even you have a concrete. And if you want to have a look, let's have a look in concrete. So what is the difference? You have the Young's modulus and Poisson ratio, and also the mass density. So the mass density doesn't matter because we are using a static analysis, but it is inside. This is simply a predefined material. So it doesn't matter if you do this or that analysis. For this predefined material, all the properties are listed here. So there are even like thermal properties, although we don't do a thermal analysis here. So for us, what's important is the mechanical property, which is the Young's modulus and Poisson's ratio. So Young's modulus is around 30 gigapascal and Poisson's ratio is 0.17. This is what is saved under concrete. So this is of course a generic concrete. So if you use a special type of concrete, then or the mass ratio to the water ratio that you put in, or if it's hardened, how many acrylamates, how much sand you have in, and so on and so on, it all changes the properties of this composite material. But technically speaking, this is a good estimation in order to begin with. So what happens if I change the material to something completely different? For example, let's choose steel. So that was something like a steel generic. So the only stuff we change is actually the Young's modulus, which is now instead of 30 gigapascal, like 200 gig, and the Poisson ratio is changed. Okay, so these two values, that's what it changes. So technically speaking, this material has these properties. I don't have to use the Freecad's version. I can also put something else, or I can even use a material editor and so on. Okay, so let's choose something. It doesn't matter a lot for us now what we choose, and I need to say okay. So we have a method in the analysis. We have the solver tools. So what type of solver do we have? We have the material that we have selected. What I need to do now is I need to define the boundary conditions. That means on the left hand side, so here I want to hold it, right here on the surface I want to hold. I need to define that I want to hold that. So by the way, I'm using Alt here in order to rotate it, because the selection here on down I have touchpad selected, so because of that I'm using Alt in order to rotate this structure. So the boundary conditions, you can see it here, model, and then we have mechanical constraints. So these constraints can be like fixed, so which is by the way this icon here, so that's the same icon. See if I come on that, so that's constraint fixed. So, or we can have here again constraint displacement. So constraint fixed means we are saying that the displacement is 0, so it's clamped. Okay, it's kind of a cantilever if you want to say that. So on one side we can think of it's fixed, so it's a cantilever. We have a beam on the right hand side, we are shearing with a force. So that's what I want to have. So I want to have a fixed constraint. So on the left, on the task, select multiple faces. So I can have, of course, like this and this fixed, right? So I can have this kind of stuff. I only want to have one face, and that's this face. This is a pretty much nice showing of this is going to be applied, right? This is also kind of what we use in technical drawing in order to mimic that this surface is fixed. Okay, that's it. I don't need to do more, so I'm saying okay. Now I have a constraint fixed, and what I want to have is on the other end I want to apply a force. So here I need to find the force. See here, constraint force, constraint pressure. I can even have something like a, technically it's a moment, right? So then we can even have, because of mass density, normally it's not important, but because of mass density you want to have its own weight, right? So we can do that as well. Normally it's neglected, because normally we put some forces on a structure and the structure deforms because of these forces. But if you have a large object, so for example you have a bridge, like a 1 kilometer huge bridge, then the self-weight is important. So you need to actually acknowledge the tons of material which is putting a significant load on its own. So then you need to put that as well. But if you have a simpler, smaller structure, that the deformation is because of the loading itself, mechanical loading itself, then you technically don't need to care about that. So this is why it is on default neglected. Okay, so I'm gonna put a force, and I can change this one, right? So, and I can say that. So now we can, let me have a look. So now we see here that the force is in the direction of the beam itself, so it's kind of a tensile force. And of course I can change the direction, so it can be also pressure. It's kind of like pressing into that. So I can also try to select the face or edge and then try to make a direction. See, so it is now directed along this face, so it's more like beam, bending beam. So if you hold here and then do a shearing force there in this direction, then this beam will bend. So let's use that one. And of course there's the load in Newton, so we have used millimeter and now we are using Newton. So that means the if you think of force per area, Newton per square meter, so we are going to have Pascal. Okay, so the total force that I want to apply on that, so I don't know about, I just said I think like 100 millimeter or something like that. It is not that big, so I'm gonna use maybe 1 kilonewton. Okay, let's use 1 kilonewton and see what happens and say okay. Okay, now we have the constraint fixed and the force. Okay, so we have defined everything what we need. So what we do now need is a mesh. Okay, so I'm going to use a mesh by selecting the cube. So it is in analysis, right? So everything was in analysis. Now I'm selecting the geometry because the mesh I'm going to put is on the geometry. So I select the geometry, and here you have two different possibilities for mesh. So one is netcan, another is gmesh. So they're both really powerful, and but we're going to use gmesh here. Okay, so I can simply say apply without thinking too much, and it will do something. This is a really coarse mesh. Okay, so I'm gonna use a finer mesh in order to do that. So first of all, the dimensions from shape, I can say 3-dimensional, but Freecad is clever enough to understand that this is 3-dimensional. I can choose, it doesn't matter. So the element order is second order. There's only first order or second order, nothing more in this simplified version of Calculix. So it doesn't matter, I can choose whatever I want. That means if I choose first order between this node and this node, the displacement is interpolated linearly. If I choose second order, then it's interpolated with a second order polynomial. So what is the difference? If I choose second order, it is computationally more heavy, but the good side is the stress, which is because of strain, which is the derivative of displacement, is a linear function. So the stress is linear. If I choose first order, so I have linear interpolation, then the derivative of the displacement of strain is constant. So stress will be constant within each element. So that's the difference. If I use first order, I can use that. Then I need to use a really nice and fine mesh. So let me do that. Let's see. So it's a really nice and fine mesh. So then with this a lot of elements, I mean that's fine, this is a lot of elements, but my computer is capable of doing that. I can calculate, or I can choose second order, then it's going to be computationally more heavy, so that means, but it will be more accurate, so that means I can have a little bit of a coarser mesh. So the accuracy of the calculation will be roughly the same. The computational time will be roughly the same as well, but it depends on how many elements do you want to use. Okay, so most of the time people use a really fine mesh. Most of the time people use a fine mesh and do a lot of elements on it because it looks cool. Okay, so there's no huge difference between them what to use. You can use both of them in this version. So let us say that's fine for me. Okay, now we have the mesh in the analysis, now we have the material, now we have the boundary conditions, force applied, and the constraint. So what I need to do is now I need to solve. Okay, so I'm going to write the input file. So you can also have a look in the input file if you want, and then run Calculix. Okay, let's have a look in the input file in order to see what is inside. So this is an auto-generated file. By the way, this file and everything is saved. You can see it here on the report view. So let me make it a little bit larger. So normally we don't really take a lot of attention, but here everything is reported. So if you look the final stuff, Calculix input file is written out in 0.2 seconds, which is really shocking news. And it is actually in the home desktop Freecad path. You remember that's the custom path, custom directory that I was selecting in the settings, and inside it just created a unnamed because I never saved. So this project is unnamed, and that is solver Calculix tools, and inside FEM mesh gmesh input inp is like an input file. So this name generation is actually coming from Abacus. Abacus is using INP as well, so they also use the same type of writing out. So first you have the nodes, so exactly also in Abacus, it's a commercial FEM program, and then you have, it's a long list, then you have the elements. So each element has 4 different nodes. So this is like each element, that's the element number 42,821 has these 4 nodes. Each node 2,559 is on the list on top and has coordinates. Okay, so that's the whole topology with elements and nodes. And then there's some more interesting part, which is like output, what you want to have as an output, and then that's end. Okay, so it's also here about units, that's important. So this is a numerical calculation, it just uses numbers, so it doesn't know about which kind of unit system that you want to use. So that means you can use whatever you want, but Freecad normally gives you an indication of millimeters, so you may think that Freecad knows that you're using millimeters. No, it's not the case. This FEM is just doing 5 times 8 is 5 millimeter, 8 also millimeter, doesn't know. Okay, so we have to make sure that all units are consistent. So we have used millimeter, okay, then we have used gigapascal for the stuff, and so you have millimeter and Newton. So that means what we are going to see as stress will be in megapascal. Okay, so that's the common use of in Freecad. It depends on the geometry. If you want to have a geometry not that small in millimeter, if you want to have like in centimeter or meter, then you have to take care about the material constants. Okay, so we have used here in such a way that everything is millimeter and newton. Then we can run it. Now I'm running it, so technically speaking we don't see a lot other than my mouse is turning, and now it's finished. Okay, so we have like 2.5 seconds, it's done, and also loading results set. So I can close. Now on the 3, So we have on top of the solver and materials and all the FEM and so on, Calculix results. Okay, so I can double click on that and we see the results here. So that's again the mesh, so we don't see any results because the result type is none. But if I want to see the displacement, I just click on that. So then I see in a simplified version the mesh and also as a color the displacement. So displacement is green, which is like a small displacement, technically zero displacement here, and it's getting gradually red. Red means larger displacement. So the results showing capabilities are fairly limited, but it's simply good. So we can have a look in that. So you can also show the displacement. So I'm showing it now, the displacement here. And now I can show the displacement by using a factor of 1. See, now we see the displacement. So it's a large displacement, by the way. It's really large. Normally we don't have this kind of large displacement. So I can even make it larger in order to show it. So I can use this slide here and make the displacement larger. So this is only for exaggerating in order to understand what happens, right? So this is not reality. This is just in order to show the results nicer. I am multiplying the displacement 7 times. So I'm multiplying the displacement 23 times in order to make it obvious what it does. If I want to see the reality, I need to use the factor 1, and that's the reality. And here in gray you see the undeformed object, and this is now, because of the forces, deformed object. The forces are on top of the undeformed one because this is where we apply the forces onto the configuration which is not deformed. And what we see here is we can, by the scale factor 1, we can see a displacement. So that means it is a large displacement. And technically speaking, so this large displacement is not the case in normal engineering applications. Only in some special cases, if you have like really thin objects, large objects and so on, you may have this large displacement. For example, maybe you remember last time when you were in an aeroplane and then you have seen the wings are really having large displacement that we see. But if you just sit on a chair, the chair is deformed, you're sitting on it of course, but the deformation, you don't see that, it's small. Because technically normally we don't see the displacement. Here we have chosen such a large force that we see the displacement here. So of course we can visualize only the displacement along x, which is technically nearly 0, and then we have y and x and y and also z. Okay, so the biggest one is y because we are using along that's here the axis. By the way, y is exactly the axis which is in the direction of the force, or force is in the direction of y. Something interesting is the Mises stress. Of course we want to see so I'm not going to show the displacement anymore. So now I'm showing the von Mises stress, which is also nice. We don't see the numbers, which is pretty not nice, but technically speaking we can do even like a calculated plot, so you can get an array list. I'm not using this kind of stuff most of the time, but this is a good way of, or quick way of visualizing the results. So here it is. So we have now seen a really simple, just a beam bending. If you do a more complicated part, and again you use the same structure, same progress of using first material and then also using the boundary conditions and then double checking the solver conditions, making a mesh on it, and then give it a go, then you are able to do some fancy simulations. It's all with FreeCAD.